Everyone thinks that the more gears a car has, the faster and more fuel efficient it is, right? From early 4-speed automatics to today's 8-speed or 10-speed transmissions in ICE cars, we have long been trained to have an intuition. Without a multi-speed transmission, the drivetrain efficiency will be relatively poor. So when the Porsche Taycan launched with a 2-speed transmission, many people cheered loudly, thinking this was the future of EVs. But today I'm going to tell you a completely counterintuitive and cruel truth for the vast majority of EVs. Adding a multi-speed transmission not only fails to improve overall efficiency, but instead becomes a fatal flaw that eats up horsepower and causes overheating. This is definitely not some cost-cutting measure by automakers, but an insurmountable limitation of physics and fluid mechanics. This video will completely shatter the myth that EVs need transmissions. Next, we will divide the deep analysis into 3 core sections. First, we'll take you straight to the extreme high-speed limit of 20,000 revolutions per minute to see how the gear oil inside the transmission transforms from a lubricant into a terrifying fluid drag, causing severe parasitic churning losses. Second, through the lens of thermodynamics, we will accurately calculate how, in the cramped space of an EV chassis, the extra mechanical structure brings a terrifying thermal bottleneck, and how this will destroy the power density that EVs are so proud of. Finally, in the third part, we will dive into cutting-edge power electronics to tell you why modern engineers would rather focus their efforts on improving silicon carbide inverters and software control than touch a single extra mechanical gear. Let's first look at the first issue: fluid friction and parasitic churning losses at high RPMs. An ICE engine's RPM is at best 7,000 and cuts off fuel at 8,000 revolutions per minute, so the operating environment of a traditional transmission is relatively mild. But an EV motor is on a completely different level. Today's mainstream permanent magnet synchronous motors or induction motors easily hit 15,000 revolutions per minute, or even start at 20,000 revolutions per minute. Future technology is even pushing towards 25,000 revolutions per minute. Under such extreme speeds, the physical properties of the gear oil inside the transmission will undergo fundamental changes. Imagine this: stirring water with a spoon is very easy, but what if you had to stir in thick honey 300 times per second? This is what is known as parasitic churning loss. At low RPMs, gear oil is an excellent lubricant. It can effectively form an oil film on the gear meshing surfaces, reducing direct metal-to-metal friction. However, when the RPM breaks 10,000 and reaches 15,000, the shear stress in fluid mechanics skyrockets exponentially. At this point, the gear oil, to the rapidly spinning gears, is no longer a lubricant, but an invisible wall. With every single revolution, the gears must overcome massive fluid resistance to cleave through the oil. If we want to install a 2-speed or multi-speed transmission in an EV, there must be clutch packs, planetary gears, or more synchronizer ring structures inside. This means the transmission will be larger in volume, and the amount of lubricating oil that needs to be churned inside will also be greater. During high-speed cruising, you might expect that shifting to a higher gear would lower the motor RPM to save power, but in reality, the complex gear sets inside the transmission are frantically churning the oil. These fluid resistance will directly eat up the torque output by the motor. In other words, the gear sets you added to pursue that tiny bit of high-speed cruising efficiency are, for the vast majority of their operating time, holding the motor back, needlessly wasting precious battery power on simply churning oil. From the perspective of energy conservation, this is completely penny-wise and pound-foolish. This leads directly to our second issue, the thermal bottleneck. Energy does not disappear out of thin air. Those churning losses just mentioned, along with the mechanical friction from multiple gear sets meshing, will all be 100% converted into heat. EV hardware design pursues ultimate power density. We always hope to squeeze the maximum horsepower out of the smallest volume. This means the motor and inverter are inherently two extreme sources of high heat, already requiring a very massive and complex liquid cooling system to service them. Let's do the math. Assume an EV with 300 kilowatts of output. If it uses a single-speed reducer, the drivetrain efficiency is about 98%. That means 2% of the energy turns into heat, which is about 6 kilowatts. 6 kilowatts of heat is already equivalent to several household space heaters running at full blast. But if you switch to a complex to-speed transmission, because the increased gears increase churning losses, the efficiency might drop to 93% or even lower. At this point, your lost heat skyrockets to 21 kilowatts. Inside a metal casing not much bigger than a showbox, continuously generating 21 kilowatts of heat is an absolute disaster in terms of thermodynamics. If you cram this multi-speed transmission that furiously generates heat into the drive module, your cooling system load will instantly max out. Gearbox overheating won't just cause the oil to thermally crack and fail early. leading to gear breakdown. More fatally, heat conducts. The high temperatures from the transmission will directly conduct to the closely connected motor stator next to it, or even onto the more fragile inverter module. To solve this extra massive heat source, engineers would have to drastically increase the coolant flow, enlarge the front radiator, and even swap in a more powerful water pump. As a result, the car gets heavier, and the power consumed by the pump also increases, all for a transmission that might save a tiny bit of power. Above 150 kilometers per hour, the entire thermal management system of the car has to suffer, taking on more weight and volume. This is a very bad deal in modern drivetrain engineering. This is also why, aside from a very few supercars, strictly made for chasing top speeds on unrestricted autobahns, or for setting lap times at the Nürburgring, regular passenger and even high-performance EVs have decisively abandoned multi-speed transmissions. Let's dive deeper into the long-term hidden dangers brought by mechanical complexity. In the industrial field, there is an unchanging truth: fewer parts mean higher reliability. ICE transmissions have undergone over a century of development and have indeed reached an astonishing level of durability, but the output characteristics of EVs are extremely brutal. To mechanical structures, EV motors possess a very violent characteristic: maximum torque at 0 RPM. The instant you press the accelerator, the motor can unleash 100% of its peak torque within milliseconds. This immense instantaneous shock is directly slammed into the transmission's input shaft. If an EV were equipped with a multi-speed transmission, the internal gear bearings and clutch friction plates would have to withstand an instantaneous torque-tearing force, several times greater than that of an ICE car. To withstand this destructive torque, every gear inside the multi-speed transmission must be made much thicker and sturdier. The materials must be higher strength forged alloy steel, and the surfaces must undergo extremely complex heat treatments. But even so, under long-term, frequent hard acceleration, the gear meshing surfaces will still suffer unavoidable metal fatigue and microscopic spalling. This not only makes the transmission noise gradually increase with mileage, but also fills the lubricating oil with metal shavings, further exacerbating the wear and tear of the whole system. Additionally, shift logic control is also a huge nightmare for EVs. When ICE cars shift gears, engine RPM drops relatively slowly, giving the transmission enough time to rev match. But an EV motor's RPM changes extremely fast. To smoothly switch a 15,000 revolutions per minute power source to another gear ratio instantly, without any obvious jerkiness, places outrageously high demands on the clutches and synchronizers. If the shift is just a few tens of milliseconds slow, the driver will feel a strong pulling sensation, severely ruining the EV's originally silky smooth driving experience. At this point, someone will surely ask, without a transmission, how do EVs balance off the line burst power and high-speed cruising efficiency? This is the key we will discuss last. The efficiency of software and electricity has already left mechanical efficiency far behind. This is an era where electronic control thoroughly dominates mechanics, rather than using complex, heavy, prone to damage, and furiously heat-generating mechanical gears. To alter reduction ratios, modern engineers choose to tackle the brain directly. That is, directly upgrading the inverter's switching frequency and control logic. We now have third-generation semiconductors, namely Silicon Carbide SiC components. 6 high-voltage and high-temperature resistance characteristics allow the inverter to operate at astonishingly high frequencies. Engineers use high-frequency, precise pulse width modulation (PWM) technology, paired with extremely complex space vector control algorithms, to every single millisecond precisely adjust the current and voltage fed to the motor stator. When you need off-the-line burst power, the inverter can instantly provide massive current, generating powerful torque that breaks the limits of tire grip. And when you're cruising on the highway, engineers use a technique called field weakening control, because motors generate back EMF at high RPMs, which impedes current from entering. Software is used to precisely control the stator magnetic field, actively weakening the rotor's magnetic field strength. This allows the motor to break past its original RPM limits, continuing to push towards extremely high speeds, while maintaining excellent operating efficiency. If you really need to balance both top speed and acceleration, automakers will directly install 2 motors with different characteristics. In today's high-end electric vehicles, for example, an induction motor on the front axle handles high-speed cruising, while a permanent magnet synchronous motor on the rear axle handles off-the-line burst acceleration. These 2 motors are each paired with a single speed reducer with different gear ratios. At low speeds, the rear motor drives the car. At high speeds, the front motor takes over, or both output power simultaneously. This is equivalent to using software-level power distribution to perfectly simulate the effect of a two-speed transmission, and there is absolutely no mechanical shifting process involved. This is the so-called distributed drive concept. As long as the motor's high efficiency range is broad enough, we only need a single fixed ratio reducer to perfectly cover all needs from a standstill up to 200 kilometers per hour. Using code and semiconductors to solve physics problems means no extra heavy mechanical structures, no complex clutch wear, no excessive churning losses, and no need to worry about the jerky loss of power during shifts. In conclusion, EVs don't need multi-speed transmissions. It's a great victory for software and semiconductor technology. This isn't cutting corners. It's an inevitable technological evolution. Multi-speed transmissions were indeed an indispensable invention in the ICE era, because the torque output band of an internal combustion engine is simply too narrow. But faced with a motor's characteristic of being in an optimal output state across almost the entire speed range, a multi-speed transmission becomes a burden. Next time you hear someone complaining about why EVs aren't equipped with transmissions, you can professionally tell them, because in a 20,000 revolutions per minute world, algorithms and semiconductors are always more reliable than gears, and much more efficient. Everyone thinks that the more gears a car has, the faster and more fuel efficient it is, right?